While most autonomous driving system focuses on developing perception methods on ego vehicle sensors, people tend to overlook an alternative approach to leverage intelligent roadside cameras to extend the perception ability beyond the visual range. We discover that most vision-centric detection methods have inferior performances on roadside cameras. This is because mainly focus on recovering the depth, where the depth difference between the car and the ground quickly shrinks while the distance increases. Alternatively, we find the height difference remains agnostic regardless of the distance, which is superior for the network to detect objects. In this paper, we propose BEVHeight by regressing ground height instead of pixel-wise, achieving accurate and robust roadside 3D object detection. Empirical results reveal that our method surpasses the best method by a margin of 4.85% on clean settings and over 26.88% on noisy settings. Limited by the height of sensors, autonomous driving faces great safety challenges due to inevitably physical occlusion and limited receptive field. Roadside perception, with the increased height compared with onboard cameras, has a longer perceptual range and greater robustness to occlusion. In this way, roadside perception is believed to compensate vehicle cases and facilitate a safer autonomous driving. Vision-based roadside 3D object detection faces two challenges. First of all, roadside cameras have various specifications, such as mounting angles and height. Then, a wider range of perceptual range means an increase in obstacle density. The principle from 2D to 3D is the core issue of vision-based 3D object detection. Depth estimation is a commonly used approach. However, when we plot the per-pixel depth on the image, we notice that the differences between points on the car roof and surrounding ground quickly shrink when the car moves away from the camera, making it suboptimal especially for far objects. On the contrary, we plot the per-pixel height to the ground and observe that such difference remains agnostic regardless of the distance, and visually is superior for the network to detect objects. In this way, we propose a novel height-based pipeline. We further compare depth and height in the following two aspects. For the distribution, we collect the distribution of depth and height for all annotations in a roadside dataset. As can be seen in Figure 7, the range of depth is over 200 meters, while the height is within 5 meters, which makes height much easier to learn. For the analysis when parameters change, we add a rotation offset along roll and pitch directions to roadside cameras. The correlation between the object's row coordinates on the image with its depth and height will be changed. As shown in Figure 8, compared with depth, the noisy setting of height has a larger overlap with its original distribution, which demonstrates height estimation is more robust. Based on the above motivation, we design a vision-based roadside 3D object detector. The framework consists of 5 main stages. Image View Encoder extracts the 2D high-dimensional image features from image. HeightNet and 2D to 3D projector achieve the projection from 2D image features to 3D volume features. We will introduce later. Voxel pooling transforms the 3D volume features into the bird's eye view features along the height direction. Detection head predicts the 3D bounding box. HeightNet consists of a context branch and a height branch. Context branch is composed of a squeeze and excitation layer to generate context features. Height branch contains 3 residual blocks and a DC layer to predict the bins-like distribution of height from the ground. The height bins follow a dynamic increasing discretization adjustable bins size. The 2D to 3D projector is responsible for pushing the 2D features into 3D volume features based on the above height estimation. We design a virtual coordinate system, with the origin coinciding with that of the camera coordinate system, and the y-axis perpendicular to the ground. We adopt a reference plane to simplify the computation. The process is illustrated in the above figure in Algorithm 1. We compare the results with state-of-the-arts. On DI or V2XI dataset, our method surpasses SOTA methods by a significant margin of 2.19% for vehicle, 5.87% for pedestrian and 4.61% cyclist. On large-scale ROPE 3D dataset, ours method is also better than the SOTA 0.97% for car, and plus 3.91% for big vehicle. In the realistic world, camera parameters frequently change for various reasons, such as maintenance and wind blows. We simulate these scenarios and observe a severe performance drop of the BEV depth from 41.97% to 5.49%. We showcase the benefit of predicting the height instead of depth and achieve 26% improvement over the BEV depth, which further evidences the robustness of our method. Next is the oblation studies. We oblate the dynamic discretization on BEVHeight dataset, as shown in Table 4. Our dynamic discretization is effective, and the height parameter alpha is necessary to achieve the most appropriate discretization. For the sake of latency, our method is more efficient because of much less height bins in the smaller height range. For the distance error, we convert depth and height to the distance between the predicted object's center and the camera's coordinate origin, as shown in Figure 11. The height estimation introduces less error, illustrating the superiority of height estimation over the depth in the roadside scenario. For the effectiveness on multi-depth-based detectors, we replace the depth in 2 detectors with our height-based pipeline. Our method achieves a performance increase of 2.19% on the vehicle for one baseline and 8.56% for the other one. For the qualitative results, on the clean setting, our method fits more closely to the ground truth than that of the baseline. Under the disturbance of roll angle, there is a remarkable offset to the far side relative to the ground truth in baseline detections. In contrast, the results of our method are still keeping the correct position with ground truth. Under the disturbance and patch angles, baseline detector can hardly identify far objects, but our method can still detect the instance in the middle and long distance ranges, and maintain a high IOU with the ground truth. For the limitation, our method is effective on cameras with high installation in the roadside scenario, but not ideal on cameras mounted on ego vehicles. We make further analysis. Figure 12 shows when the height prediction is equal to the ground truth, detection is perfect for all cameras. If not, for the same height prediction error, the distance between the predicted ground truth is inversely proportional to the camera ground height. We collect around 13,000 sequences from the camera mounted on a moving truck with a ground height of 3.14 meters, and annotate the 3D boxes. As shown in Table 8, we observe that our method again surpasses the depth-based state-of-the-art by a large margin, evidence the performance is a camera height. Our contributions are concluded as follows. We take the advances and challenges of roadside cameras into account and design an efficient and robust roadside perception framework. We implement a lightweight height net and design a novel height-based projection module to achieve the projection from 2D to 3D effectively. The proposed detector achieves art results on BEVHeight and ROPE 3D dataset, and up to 26.88% improvements on robust settings, where external camera parameters change.